Hi, I'm Fernanda Pereira from the Federal University of Minas Gerais in Brazil, and today we shall talk about how to prove preservation using Twelf. Here's a statement of preservation in the Twelf syntax, naturally. We are saying that if an expression e evolves to expression e prime right here, and that e has type big T, then e prime will have type big T as well. If we try to prove preservation, simply loading this script, we will get an error. By now, probably you know what this error means. So how can we fix this error? We need to write the proof. So for each possible way to evaluate a rule, we must show that preservation ensues. We have 11 cases to verify. Let's go over some of them. If we use eval succ to evaluate the expression, then we know that this term has the shape succ of n. In this case, the only rule that can type check this term is check succ. Now we need to plug this fact into the theorem of preservation. How to do it? Here's the proof. Don't worry if it seems complicated. We shall go over the details. Notice that we are using induction. It's easy to see that because of the implication at the end of the proof with this inverted arrow right here. So here's the theorem in pictures. So the evaluation rule eval succ requires a premise, which we have called eval. The type checking rule check succ also requires a premise that we have called check. From the open rule eval, we know that t goes to t prime, and from the open rule check, we know that t has type net. Using induction, we conclude that t prime also has type net. Let's call this fact check prime. We use check prime as a premise of check succ to show that succ t prime has also type net. What about if we use pred 0 to evaluate the expression? In this case, we know that this expression has the form pred of 0 goes to 0. And we also know that check pred was the typing rule used to type check the term. How can we plug this fact into the theorem to derive that the resulting term, that is 0, has type net? In this case, we don't really need any induction. We simply use the rule check 0, because the resulting term that we get from evaluating pred of 0 is 0. And 0 has type net by rule check 0. If we use instead eval pred s, then we know that we have pred of succ of n evolving to n, and that the only rule that type checks pred of succ of n is check pred. Do you know how to finish the proof? Think. Will we need induction? We don't actually. The thing is that we have pred of succ of n going to n, and that pred of succ of n has type net, because succ of n has type net, which requires n to have type net. So we use this fact to conclude the proof. I have a pictogram here. If you want, stop the video and check how each premise in Twelf matches the premise on the paper. See how check with an uppercase C I mean, which is the name of the fact that says that n has type net is used in the proof. Let's show preservation assuming that eval pred was used this time. We know that pred of t goes to pred of t prime because t goes to t prime. And we know that pred of t has type net because t has type net. Do you know how to finish the proof? We will need induction. Here's the proof. We do need induction, as you can see due to the implication of the rule. That's this inverted arrow here. Can you stop the video and try to figure out how induction is used? What are the facts that enable us to use induction in this case? Would you like to write the proof for eval iszero z? In this case, we know that iszero 0 goes to true, and we know that iszero 0 has type bool, and that 0 has type net. How do we plug these facts into the theorem to conclude the proof? That's rather simple, actually. Use check true. Remember, we know that iszero 0 goes to true and that the type of iszero 0 is bool. We need to show that the type of true is bool, but this fact is given by the rule check true. If we have eval iszero s, what do we know? We know that iszero of succ of t goes to false. How do we conclude the proof? Notice that in this case, you will not need induction. We simply use the rule check false. Again, we know that iszero of succ of t goes to false. We know that the type of the term is bool, the original term I mean, due to the rule check is 0. And the rule check false gives us that the type of false is bool. If we have eval is 0, then we will need induction. Would you like to try to build a proof? First of all, if the rule is eval is 0, then we know that iszero_t goes to iszero_t prime. And iszero_t can only type check through rule check is 0. In this case, we know that t has type net. Can you plug this fact into the theorem via induction? Here's the proof. Notice how we are using induction to conclude a fact called check prime, right here. And how we then combine check is 0 with check prime to finish the proof, right here. If the rule used in the evaluation is eval if true, then we know that we have an if then else clause. We know more. We have if true, then t2 else t3 going to t2. And the type checking rule must be check if. How do we conclude the proof? Will we need induction? Stop the video and think about this question. Will we need induction? Not really. We know that the term is going to t2, but we already know that t2 has type t, as this premise is part of the rule check if. Then we just need to use this fact to conclude the theorem in this case. The proof of eval if false is totally similar. Would you like to demonstrate it? You have the necessary definitions here. I suggest you to stop the video and try to show how preservation ensues in this case. Here's the proof. That's a simple matter of using the premise that says that T3 has type big T. Now our last case, eval if. Would you like to try to write a proof? I can tell you what we know. We know that if T1 and T2 else T3 goes to if T1 prime and T2 else T3. We also know that the type of T1 is bool, the type of T2 is big T, and the type of T3 is also big T. So how do we conclude the proof? In this case, we will need induction. By the way, the order of the premises when we write a theorem is the inverse of the order in which the premises appear in the definition of rules. So in this case, inside the red box, check T1 is the premise that says that T1 is bool, right here. Here's a correspondence between the premises and the definition of check if and how they are used in the theorem, so they are inverted. And with this last example of a proof, we conclude our class on 12. There are many mechanical theorem provers. 12 is just one of them. You might check others like Isabelle, Coq, and Idris. Idris actually works also as a general purpose programming language. Well, the other theorem provers work like that as well, but it's just that the syntax would be a little bit cumbersome. And do know that today we have even whole compilers that have been formally certified, like CompCert, which is this work from Xavier Leroy. And with that, we conclude the class. Thank you.